Hello, everybody. Let's talk about the vapor pressure. So in class, we started our discussion on vapor pressure by looking at observing a quick demo. And in the demo, we took a paper towel and we put a couple drops of rubbing alcohol and a couple drops of water on the paper towel, and we were observing which thing is going to evaporate first. And as we predicted, rubbing alcohol evaporated first. So then we were investigating why did that happen. So to answer that question, we first off looked at the difference between evaporation and boiling. These are the two words that we very often use interchangeably. Uh, the similarity between the two things is that both of them represent the same phase change, and that phase change is vaporization. In both evaporation and boiling, we are going from liquid phase to gas phase. However, evaporation can occur at any temperature. There doesn't necessarily have to be a specific temperature to start evaporation. It can, in some cases, it even occurs at room temperature. Boiling, however, is temperature specific for each type of matter or each substance that we are looking at. And then evaporation, for the most part, only occurs at the surface, but boiling actually occurs throughout. So when you start boiling something, you observe the bubbles at the bottom, and then eventually those bubbles also travel up, so the entire thing is boiling. And then we talked a little bit about how substances evaporate. So we had these two questions to think about. The first was, if we leave water on the desk, we would not expect that water to be there in the morning, and that's because on the desk we have more surface area, so there would be more evaporation. However, if you leave a water bottle in your car, you would expect to see the water in that bottle when you return to your car the next morning. And that's because we can't claim that there was no evaporation in the bottle when it was sitting in the car. Maybe there was, but it's a closed system, so all the water that was evaporating eventually condensed back. So we still see the same amount of water that we had. So all of this is impacted by the vapor pressure, which in general is just the pressure of the vapor above a liquid, and it tells us how much something wants to be a gas. And by something, we mean the substance that we are observing. So if the vapor pressure is very, very high, that means this thing really wants to be a gas. And so remember that gases have weaker intermolecular forces. So if something is a very high vapor pressure, a lot of that substance is becoming a gas. So it's going to have weaker intermolecular forces. So there's like that indirect relationship between vapor pressure and intermolecular forces. So in order for something to begin boiling, and this is super important to remember, anything cannot start boiling until the vapor pressure is at least equal to the atmospheric pressure. So your vapor pressure should be equal to or greater than the atmospheric pressure for something to begin boiling. Before that, when your vapor pressure is lower than the atmospheric pressure, the thing exists as a liquid. It cannot start boiling or evaporating. And then we are given some information about vapor pressure of four different liquids in table H. So we talked about table H a little bit. If you look at this table, the first piece of information that we can get is the standard pressure. Your standard pressure is where any liquid or any liquid out there boils just normally at the standard pressure. Uh, so that pressure is 101.3 kilopascal, which means in order for the liquid to boil at this temperature, we don't need to like change any conditions or exert any external pressure. Um, so if you look at water at 101.3 kilopascal, the temperature that you see for water is 100 degrees Celsius, which is the normal boiling point of water. Um, so the next thing we did was we looked at two different liquids. So we are looking at propanol and water now. Here are the structures for both of them. And we looked at their vapor pressure at 65 degrees Celsius. So at 65 degrees, there we have water and there we have propanol. So water has a vapor pressure of around 23 kilopascal. Propanol is around 133 kilopascal. And then looking at their structures, we talked about their intermolecular force. Water is going to have hydrogen bonding because it has the bond between hydrogen and oxygen. Propanol is also a polar molecule, but because of no bond between either hydrogen and oxygen, fluorine, or nitrogen, it's going to have dipole-dipole attractions. So hydrogen bonds are stronger compared to dipole-dipole forces. Therefore, remember how we said that there's an indirect relationship between intermolecular forces and vapor pressure. So if something has weaker intermolecular force, it's going to have a higher vapor pressure. And if it has stronger intermolecular force, like water, it's going to have a lower vapor pressure. That means this thing does not really want to be a gas. So, which is why it takes us longer to boil water at 101.3 kilopascal compared to propanol. And another thing that this graph tells you is the relationship between vapor pressure and temperature. So notice how all of the curves are going upward, starting from 0. So that tells us that as the vapor pressure is increasing, the temperature is also increasing, or vice versa. As the temperature is increasing, vapor pressure is also increasing. So that leads us to the discussion about temperature. Remember that temperature is the measure of the average kinetic energy. Kinetic energy is the energy of movement. So if the particles are moving very fast, that means the temperature is very high. So when we increase the temperature, we are actually increasing the kinetic energy of the particles. Um, so it does make sense that when the particles are moving at a very high speed, more of those particles are going to become a gas, because in gases, particles move faster compared to liquids. So that is why we have that direct relationship between temperature and vapor pressure, because more speed of particles, more particles becoming gas. And finally, we wrapped up our discussion on vapor pressure with this quick question, that let's say you FaceTime your friend who lives on the mountains of Colorado, and you live in New York City. Both of you start cooking pasta at the same time. Whose pasta is going to cook first? And the answer to that was your friend's pasta, who is on the mountains of Colorado. And that's because as you go higher up on the mountains, or as you move away from the sea level, or as your altitude increases, altitude is the distance from the sea level, the atmospheric pressure decreases. So on the mountains, the atmospheric pressure is lower. So it is easier for the vapor pressure to be like equal to the atmospheric pressure, or become greater than the atmospheric pressure. It's going to take less time for the vapor pressure to like become equal to the atmospheric pressure. So whatever we are trying to boil, that thing starts boiling faster. Comparatively, if the atmospheric pressure is very high, it takes a longer time for the vapor pressure to equal the atmospheric pressure in order for the thing to start boiling. And that was it for the vapor pressure.